Howdy guys, welcome back to our video on gases with the kinetic molecular theory. The video is going to focus mostly on the theory, not really the math. If you remember at the beginning of the gas laws video, I gave you 2 points that we had to assume were true. Well, there's actually 4 points that we know are true, that we accept as true, just so the math will work out right. And the particles are so small that their volume is considered to be zero, because the distance in between them is just so large that we just consider those particles as having a volume of zero. They're always in constant motion. I showed you that one. And they do not interact on each other at all. We assume that they just don't interact and they're independent, and that the average kinetic energy of the gas particles is directly proportional to the Kelvin temperature. So the kinetic energy and the Kelvin temperature are directly proportional, meaning they both go up at the same time. The real reason why we understand this theory and we assume that the gases will work this way is so the math will work right, but it also will help you explain away the error in your lab, because you will get some kind of buffer error, and just understand that your math was based off of an ideal gas, but you measured a real gas. Since kinetic energy and the temperature are directly related, we're actually able to understand it in a math equation. We can see kinetic energy equals 3/2 RT, and but this R is a different R that's on the formula chart, and you have to commit this number to memory. It's not going to be on the formula chart, and the units are in joules per Kelvin mole. Because the units of kinetic energy are actually in joules per mole. For kinetic energy in chemistry, we're looking at joules per mole. So you need to commit this formula, and this value of R to memory. But this equation is on your exam. The kinetic energy is 1/2 the mass times the velocity squared. So the larger the mass, the greater the kinetic energy, and also the greater the velocity, the larger the kinetic energy. Since those real gases collide with each other a lot, we assume that they didn't in our math, but since they do collide with each other, their mean free path is going to be in there. And we have to have, and this will actually make a huge variation in how fast the molecules will move, depending on how light they are, how fast they are. So if we look at just one gas molecule as it moves in a container, it's just bouncing around freely, and the mean free path would be the average of all of those gas molecules as they bounced around. And this is just a plot of the number of molecules versus their velocity. And this is only one gas molecule, so you see one big peak right here. And it's more useful whenever you see it like this as a Boltzmann distribution, when you can look at one gas molecule that has different temperatures, and they will spread out in a different path length. So we're looking at the peaks right here. At a low temperature, at a lower temperature, the velocity would be much slower. The average velocity would be much slower, because the average velocity would be where this peak is. And then at a higher temperature, the velocity would be higher, and even higher at an even higher temperature. And you can also see a Boltzmann distribution based on different varieties of molecules, and you'll see that typically three different curves, and the one on the left would be The sharper peak at the beginning would be the lighter gas, and the more flat peak would be the heaviest gas. When I say the lighter gas, I mean one that has a low molecular weight, something like helium. Helium is probably, or hydrogen are the lowest ones. Something very dense or very heavy like argon would have a slower velocity. So if I have two gases that are mixed and introduced, if I introduce them into a container, they are going to diffuse. They will start to mix. And the effusion is the passage through a pinhole that you can see in this picture coming right up. This picture where this would be effusion, where they're passing through here. Um, yeah. This will follow a formula that's not on the AP test. The actual math is not on the AP test, but the effusion, and diffusion are the concepts are there, where they're based off of their molecular weights. And it makes sense that the lighter gases will diffuse faster because they're smaller, and they also have higher velocity. So that would make sense why they would diffuse faster than a heavier gas. As you can see, two different gases are introduced in a YouTube, or not a YouTube, in just a straight tube, where we have one cotton ball soaked with ammonia and one cotton ball soaked with hydrochloric acid. Though that hydrochloric acid will actually still make some type of gas. This is a heavier gas, so it will diffuse slower than the ammonia. These two will react with each other in an acid-base reaction right here, and you'll be able to visibly see a ring. So you would think that two gases would, as they're introduced, would meet in the middle, but that turns out not to be the case. The lighter gas will win the battle and will move farther. So I want you guys to remember that again, that the real gases will behave ideally at low pressures and high temperatures. And just remember summer vacation, because students always behave better at low pressures and high temperatures, which is summer. There's less interaction of particles at the high temperatures, just because they're moving too fast. So that's why that would happen. Now, the text that's displayed here is talking about the high pressure system, and go ahead and give that a read. But remember, they behave better ideally at low pressures. So there's actually an attraction of force with the high pressures, and that would negate the ideal real gas law. There's more attractive forces for large and complex molecules. So some and polar molecules, those that will actually tend to want to attract to each other. The attraction of forces as the gas particles will actually attract to each other just is called the van der Waals force, and we'll get into that later in another unit and another video. But that will is something to remember, but it's not tested on the AP test. This formula right here. But it will it helps explain how the gases will still maintain some kind of stability, vibration, even at the lowest temperatures possible. Temperatures very close to absolute zero. So supercooled helium will still vibrate just a little bit due to this van der Waals equation. That's what that math equation says. So don't get too overwhelmed by this thing right here. I wouldn't stress too much on it. Just remember that there's an attraction of forces. And thanks for watching, y'all.